Okay, let's see if the camera's in focus. There we go. Now, we want to show that the derivative of the Laplace transform of f of t is the Laplace transform of t f of t. Negative is the Laplace transform of t f of t, and we'll see where all that comes from. Well, to do this, let's just write down what we mean by the derivative of the Laplace transform of f of t. That means the derivative with respect to s of the integral from 0 to infinity, etc. Okay? Now note that s is not your variable of integration. S doesn't appear as any of your limits. So, using a little bit of second semester calculus, we can write this as the integral from 0 to infinity of f of t times the derivative with respect to s of e to the negative ts dt. And this is totally harmless. Again, s is not your variable of integration, and the limits in the integral don't depend on s. So, with respect to s, well, we can do this. Okay. So, if you believe me, and I'm not going to try to go into deeper justification, it'd be confusing. This becomes the integral from 0 to infinity of f of t multiplied by negative t e to the negative ts dt. And then we can rewrite that as the integral from 0 to infinity of negative t f of t e to the negative ts dt. But now I put parentheses around the tf of t if I want to. Now we can see that we just have the Laplace transform of the tf of t function. And negative. Okay. Okay, well, that's easy. That's pretty slick. Let's just apply it. Okay, let's say we want to find the Laplace transform of t sine of t. Now we can look up a formula in a table of Laplace transforms, but this is so easy that we should be able to do it. Well, now if the Laplace transform of t f of t is the derivative with respect to x of the Laplace transform, then the Laplace transform of t f of t is the negative of this derivative. We know the derivative of the sine of t, so let's just write it out a little more formally. Okay, this is a Laplace transform of t f of t where f of t is the sine of t. So this is going to have to be equal to the derivative with the negative derivative with respect to x of the Laplace transform of f of t. That was an unnecessary parenthesis there, but we'll live with it. Okay? And the Laplace transform of f of t is the Laplace transform of the sine of t, and presumably by now we are pretty familiar with the Laplace transform of the sine of t, and that's 1 over s squared plus 1. And the derivative now of 1 over s squared plus 1, very straightforward. Chain rule, your derivative of s squared is 2s. And your derivative of the reciprocal function is the negative square of the reciprocal function. So the derivative, whether you use that or the quotient rule or whatever, it's easy to see that the derivative of this is this. Except, of course, the derivative of this thing is negative of what I have here. Since we have a negative out here, though, we end up with a positive. Okay, so there it is. And there's a derivative, or the Laplace transform of t sine of t. If we wanted the Laplace transform of t squared sine of t, well, we could do the second derivative. Okay, every power of t gives us another derivative. So you could see what would happen with the second derivative and the third derivative and so forth. It would get more complicated because now you don't have a constant in the numerator, so the thing gets a little bit out of hand. But you can eventually see a pattern to the way the integrals build and come up with a formula for, hopefully, for the Laplace transform of t to the n sine of t, just by repeated application of this theorem.